Okay, welcome back. This is the third and final of our videos concerning electron arrangement and the evidence we get for that. And this third video is referred to as successive ionization energy. And this is the energy needed to remove one electron at a time, one by one, from 1 mole of gaseous atoms. And of course, the ionizations will take place from the outside outer shell first, working inwards towards the nucleus. And we, if you like, strip off the electrons one by one. Each time, of course, the number of protons in the nucleus stays constant, but the number of remaining electrons gets less one at a time. So the remaining ones have more nuclear attraction to pull them in, which is no wonder why the ionizations that we carry on when we keep ionizing, keep removing electrons, always get bigger each time. So the information that this gives us is really directly helpful when it comes to looking for when we've emptied a shell and we start another one, when we go from an outer shell to an inner shell, because we should get closer to the nucleus each time that happens. So we'll see what happens to the ionization energy values if we take our very simple example, which we showed you earlier on in the video number 2, the arrangement for carbon. So I'm going to show you the ionizations successively when we do them all for one particular atom, and this of course is carbon. Like we've seen before, we've got our carbon with its 6 protons, 6 neutrons, mass 12, and we've got the 6 carbon electrons arranged, as you can see, 2 in the first shell closest to the nucleus, 4 in the second shell further out from the nucleus. And we're going to ionize the same things you've seen before by firing high energy electrons at my carbon atom gaseous. Then I can remove the electrons one by one. So when we fire our first electron, we knock out the first electron from the carbon outer shell. There it goes. And we display the ionization energy on our bar graph. And remember, we've seen this one before, 1087. That's the first ionization. Now, when it comes to do the second ionization, let's think about the equation. We will be starting from carbon 1 plus gas, and then we'll be ionizing again. That will give us carbon 2 plus gas with the loss of a second electron. Or the third ionization would be when we go from carbon 2 plus gas to carbon 3 plus gas with the loss of a third electron. So remember, these are always gaseous and they always go up 1 electron losing at a time. So that was our first ionization. So when we do it again and knock the second electron out, there that goes, we get a second value. This time 2353, an increase in the amount of energy needed, as you can see, to go from C1 plus to C2 plus. Like I said, we still have 6 protons in the nucleus, but then we only had 5 and now we've got 4 remaining electrons. So the amount of protons per electron, if you like, is getting stronger each time. We're still in the outer shell and we've still got 2 electrons to move. So let's get rid and ionize a third time. Here we go. As you can see, 2 plus gas has now become 3 plus gas, and the ionization energy has approximately doubled. And it's done that 3 times, from 1,000 to 2,000, 2,000 to 4,000. So it's gradually increasing in a nice, reasonable fashion. And we have now got to carbon 3 plus by ionizing it a third time. Still got more to go in the outer shell, so let's do that one. And the fourth ionization, 3 plus to 4 plus, and the increase is another couple of thousand on the previous one. And so we've got rid of all 4 outer electrons, and what we're left with now is a C4 plus ion, which of course is electronically the same as helium, which of course is a full 1s2 shell. So although we've got a C4 plus gaseous ion, we've still got 6 nuclear protons pulling in, holding on to those remaining 2 electrons. Now helium only had 2 nuclear protons. So we've got 4, we've got twice as many nuclear, 6, we've got 3 times as many nuclear protons to pull in those remaining 2 electrons. Unsurprisingly then, the next ionization will be very significant. And let's knock the 5th electron off, this time from the full innermost shell closest to the nucleus, with the same 6 protons hanging on to them. There it goes. And what are we going to get? Oh my goodness. I hope you noticed it. The significant big jump, a very large increase in the ionization. Well, of course, we know why, because we're now removing an electron from a full inner shell. In fact, the closest shell to the nucleus. So it's got considerably more difficult because, of course, the nuclear attraction is still 6 protons. And now we've only got 1 electron left. The 5th electron removal, the 5th ionization, broke into a full inner shell. The first 4, as you can see, were relatively easy to remove. Those were the outer shell 4 electrons. And then the last 2 must be the innermost 2, right near to or closest to the nucleus. And of course, with the greatest nuclear attraction and absolutely no shielding whatsoever. So this is no wonder the ionization value has such a large increment. One more to go, so let's completely strip that last electron off. And unsurprisingly, right, crikey, there goes your bar, which again is a very big increase. And of course, unsurprisingly, because that's the innermost 2 electrons closest with the same 6 protons. And now, of course, there's no electrons left. And it's taken all that energy to remove them one by one, as you can see in the steps. The significant increase, that big jump, occurred between the outer shell 4 and the inner shell 5th ionization. So there's something important about having 4 outer shell electrons, and of course that tells you carbon is in group 4 of the table. Aha, patterns. So here are our ionization values. As you can see, the first 4 were relatively easy. Those are the outer shell electrons. Then we get the big significant increase when we've gone from an outer shell to a full inner shell. That big jump is very revealing because to the left of the big jump tells you how many electrons in the outer shell, therefore the group number, group 4 for carbon, as you can see, 4 easy removals. And then it also shows you on the right of that, the 5th ionization, where the big jump has occurred, that must come from a full inner shell of electrons. So where the big jumps occur tell us where we've moved from one shell to another. Okay, so let's just have a little look at the same idea, but this time we've put the ionization energies successively for aluminium in a table. Just so you're aware of what the ionization energies are and the equations that would represent them, we do get asked to, for example, write an equation for the 3rd ionization energy of aluminium. And that would be going from Al2 plus gas to Al3 plus gas plus electron. Remember, whichever ionization you're doing is going to be the product ion that you're making. So the 4th ionization would make Al4 plus gas and so on. Now the successive ionizations are shown in the table, as you can see, and the numbers are getting rather silly. So what we do nowadays, and what is much easier for us to do, is to take the log to base 10, that's the logarithm to base 10 of those ionization energy values. And the numbers change quite considerably, but of course it's the same relative increases, but the log scale condenses it nicely so we can see it easier on a graph and we can represent it and look at it. Remember, when we do successive ionizations, we are always working from the outside inwards. So the last two electron removals are always the 1s2 and 1s1 electrons closest to the nucleus. So no wonder the ionizations will always increase. Of course, the number of nuclear protons in aluminium stays at 13. As we remove the electrons one by one, 13, then 12, then 11, then 10, and so on, the number of protons is staying the same, the electrons are getting fewer, and again, of course, closer as we strip them off. So the nuclear attraction and the shielding come into play here. The nuclear attraction is going to be constant, but the shielding is going to diminish as the electrons are stripped off. And of course, the radius is going to shrink as the atom, we go from outer shell to inner shells. All of these factors will make the ionization energy substantially bigger at each successive ionization, until we get to the key ones where we go from one shell to another. If we just look at the numbers in the aluminium ionizations, 578 for the first one, then 1817, 2745. So the first three relatively easy increases, not really doubling much. And then we get from 2000 to 11,000. Now that's a significant increase, a big jump, if you will. So after the first three, which are outer shell removals, the fourth one is from the full inner shell of electrons. And of course, there are 8 of those, S2P6. So if we carry on removing electrons, the fourth one, the fifth, the sixth, the seventh, the eighth, the ninth, and the 10th, and the 11th, then we have now emptied the second shell, and we have got rid of the S2 and P6. Remember, the first 3 electrons out were the 3s2 and 3p1. Then the next 8 were the 2p6 and 2s2, getting closer to the nucleus. And so the last 2 are the 1s2 and 1s1. We've worked inside from 3p1, working backwards to empty our electrons. Well, let's have a look at the graph when we plot this using the log values in a moment. There is a table, and this is quite a handy exercise for you to do and just to check yourself. So what I want you to kind of do is take a look at the electrons. These are the successive ionizations for everybody up to calcium. Well, I know it's just a load of numbers, but I want to pick out a couple of interesting ones to start with. So first of all, let's look at beryllium, group 2. First of all, first ionization 900, second ionization, well, 1800, more or less doubling. But the third ionization, 14,000. That is a big increase. So if you like, you highlight a pen or mark the gap here, the division between the second ionization and the third is where the big jump occurs for beryllium. To the left of the big jump are the electrons in the outer shell, and there are, of course, 2 of them. And then we break into a full inner shell with a big jump as a consequence. Now, if we go to the next group 2 element after beryllium, which of course is magnesium. So let's jump down to magnesium and look at its numbers. 738 is less than 900. Remember, first ionization, the ones in the yellow column, that decreases down the group because magnesium has more protons, but it also has more electron shielding. And the radius of magnesium is bigger than beryllium, and so the outer electron is held less strongly or attracted less strongly. So ionization decreases. That's going to be exactly the same, of course, for the second ionization, 1757 for beryllium, 1451 for sorry about that, 1451 for the magnesium. So the ionisation decreases for the same reasons. We come to the third ionisation for magnesium, and again we get a substantial increase. There is the big jump for magnesium. Let's choose a different element. I'm going to look at nitrogen. So if we pick nitrogen here, 1,400 is roughly doubling, 2,800, 4,500 and 7,400, 9,400, whoa, 53,000. A big increase here. Well, you often get ionisation sequences, successive values like this, and you have to make a simple deduction. What group is the element in? So find the big jump and count the number of ionisations to the left of that. Nitrogen has 1, 2, 3, 4, 5 lower values, and of course the big jump from 9,000 to 53,000 is because we are entering a full inner shell. So the sixth electron removal is from an inner full shell. So nitrogen must belong to group 5. It has 5 outer electrons. If we pick the same group as nitrogen and the element under that is of course phosphorus, we should get the same significant increase between 5 and 6. Well, of course we do. This again confirms the periodic table is in the right order and that the patterns that we see for ionisation are because of the arrangement of electrons in shells and subshells and orbitals. So it's quite a useful exercise to just run across these and pick up the big increases. And let's go to magnesium again, right in the middle. So we got our first big jump after the outer 2 electrons, that's the 3s2 and 3s1 respectively, were removed. And then we start on the second shell. And remember, we begin with the highest energy electron, 2p6. That is a second shell as opposed to a third shell. That's why we had a big jump there. So this is 2p6, keep going backwards, 2p5, 2p4, 2p3, 2p2, 2p1. Then we have the 2s2 and the 2s1. The next big jump, look, from 35,000 to 170,000, a massive increase. There's a second big jump in the same sequence. So if we take our sequence of magnesium, we got our first big jump when we remove 2. We get our second big jump when we remove another 8. And of course, we've got our last 2 innermost closest to the nucleus electrons. So if you want to write this in the reverse order, we've got 1s2, 2s2, 2p6, and then of course 3s2 is your electron arrangement for magnesium. This is why we can be so sure about our subshells, shells and orbitals, because the ionization energy numbers back that pattern up superbly. And again, a nice little exercise. It's easy to pick out elements in which group they are. The number of ionizations before the big jump tells you the number of electrons in their outer shell. The same occurs when you compare 2 elements in the same group. Then, of course, as we saw when we looked at the ionization pattern, then unsurprisingly, if we look at lithium, 500 to 7,000, then sodium, 496 to 4,500 is decreasing, and then potassium 419 to 3,000. So again, that backed up nicely why we would expect ionizations to decrease down a group. Remember, the increased protons is outweighed by increased shielding, and it's simply down to the fact that the atoms are bigger. The outer electrons are further from the nucleus and easier to remove. So all of our periodic explanations and all of our ionization energy evidence gives weight to our understanding of our electron arrangements. And so just to take a couple of others, from our table. So I'm going to pick out a couple of elements and put all their numbers in and plot them as a log of ionization energy values. And if we take the successive ionization energies for calcium, then the plot is quite substantial, but it makes, when we do the logarithm, log to base 10 of them, then of course it makes the size increments less obvious, but it does make the graph easier to understand and see. So here comes the log of the ionization, successive ones. So this is the removal of all 20 of the calcium electrons. Now be careful to remember which way round we do this. We start from the outermost electrons, that's 4s2 and then 4s1. We get our first big jump after the removal of those two electrons. And the big jump, of course, is this one here. Now that big jump is because we've gone from removing the outer two, remember it was group 2 because it's got 2 electrons before the big jump, which of course is the third ionization, and that must come from the next inner shell, which of course is 3p, work backwards. So from 4s2 and 4s1 we got the 3p6 electron out, and then work backwards, 3p5, 3p4, 3p3, 3p2, 3p1. Now, I just want to go back to that because I know it's not so obvious, but after that 8th electron, the 9th one, it's not so clear on the log graph, but it's definitely there. We do have an increase out of pattern with the change from the 3p to the 3s. These two electrons, number 9 and 10, are the 3s2, 3s1 electrons, that now completes shell 3. We get a big jump again as we go inner to shell 2. And remember, this is 2p6, 2p5, 2p4, 2p3, 2p2, 2p1. Slight increase to 2s2 and 2s1. I'm sorry, I've done that wrong again. Let me find that back. A slight increase, 2s2 and then 2s1. And then we've got another big jump as we go to the innermost, closest, the last two electrons, numbers 19 and 20. So if you look at the numbers that we've written to show the number of electrons being removed, if we work the other way backwards from the inside outwards, 2, 8, 8, 2 would be your GCSE way of writing electron arrangement for calcium, or for ours, it would be 1s2, then the 2s2, the 2p6, the 3s2, the 3p6, and the 4s2, which is how we would write it. And you've seen this already. This is our same idea, but this is the arrangement of successive ionizations for aluminium. And again, it just means I get a little bit less detail on the graph and it's easy for you to see things. So for aluminium, with 13 protons and 13 electrons, we start off with the outermost electron, which of course is the 3p1 electron. This p electron, which remember is slightly shielded and further from the nucleus than the 3s's, is why there was a little dip in our first ionization graph for aluminium. The 3p electron, let me repeat, you do need to understand the 3p1 electron is slightly further out from the nucleus, so less strongly attracted, and is shielded by a full 3s subshell, which, although not a full shell, does offer some shielding. So this makes the electron arrangement for aluminium slightly less stable and the ionization slightly easier. Nevertheless, if we take our remaining ionizations for aluminium and work inwards, so 3p1 is the outer shell, most outer 3p electron, then we get the 3s2 and 3s1 that completes the outer shell 3 electrons. And of course, after that, we get a, well, it's not a big jump on the log graph, but it's certainly a big increase compared to the others. We get an increase significantly here, which I've shown with the red line, which marks off the outer shell of 3 electrons from the inner shell of shell 2. And again, if we take the ionizations one by one, 2p6, 2p5, 2p4, 2p3, 2p2, then 2p1, the last two of these are the s orbital ionizations, 2s2 and 2s1. Then we get into the innermost shell, another big jump, of course, and 1s2 and 1s1. They do ask you questions on this kind of thing, like which ionizations are from s orbitals. Well, of course, if we look very carefully and think about it, ionization 2 and ionization 3 are removing 3s2 and 3s1 electrons. And then if we carry on going, ionization 10 and ionization 11 remove two more s orbital electrons. And if we were showing the whole thing, well, of course, the last two, 12 and 13, are also from s orbitals. So do be careful. Remember, you're working from our configuration, which is from the inside outwards. But here, successive ionizations work from the outside inwards. The last two are always the most strongly attracted because they're closest to the nucleus. And of course, would have the most protons pulling them in, and the least amount of shielding because the other electrons have all been removed. So the features which explain this graph and the variations within it are all down to our arrangement and understanding of electrons in subshells, shells, subshells, and orbitals. And there, of course, is the same idea for calcium, working from the first ionization, which is the 4s2 electron. Two are easy removals before the first big jump, so it's in group 2. And then the first big jump is when we remove the 8 from the 3p and 3s respective subshells. Another big jump to go to the 2p and 2s subshells. And the last big jump to go to the innermost first subshell, which of course is the s subshell. So that pattern, as you would write it, 2882, we would write it working from the inside outwards using subshell notation: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 is our electron arrangement for calcium. And finally, for sulfur, just so you can see from the big jump you can pick out between ionization 6 and 7. That's because the first 6 ionizations must come from the outer shell, so sulfur lives in group 6. 6 easy ionizations, the 7th one coming from a full inner shell, with, of course, the outer electron arrangements. Let's see, we would write sulfur work from the innermost shell outwards. We've got the 1s2, then we've got the 2s2 and 2p6, then we've got the 3s2, and the next 4, of course, are 3p4. So the 6 outer shell electrons for sulfur are working backwards: 3p4, 3p3, 3p2, 3p1, 3s2, and 3s1. Then there's a big jump to our second shell. That concludes my little look at our electron structure and the two forms of ionization energy, the idea of electrons in shells, the idea of the amount of energy needed to remove them, the factors that affect it, number of protons, nuclear attraction, electron shielding and the radius, and the evidence that successive ionizations gives us to back up our model of electron arrangement clearly, which is a nice and understandable and repeatable pattern. So I hope those videos have helped you and that you can refer to them or look at them again to revise or to help you work your way through what happens. So thanks for watching, and bye-bye.